Hello, good afternoon, everyone. My name is Kris Overholt. I'm a Senior Product Manager at Anaconda, and today we're going to talk about architecting Anaconda Enterprise deployments. And a lot of this comes from our customers' use cases of what does it mean to have a repository, what does it mean to have people basically working on a data science development platform, and how can we help you get that up and running in production. So about me, I've been at Anaconda for a little over 3 years now. Before that, I was very hands-on with Python, even in the pre-Anaconda days, doing things by hand. I have a PhD in civil engineering, and I worked with distributed systems, managing 500-node clusters, Python, R, all the dependency pains that we've all experienced. I worked at National Institute of Standards and Technology, Southwest Research Institute, really found the common problem of how do folks get up and running with essentially things that have Fortran dependencies, C dependencies, Java dependencies, that really just want to get work done. Especially on a large cluster, and utilize that. And so I work primarily with Anaconda Enterprise, focusing on enterprise operational data science workflows and making sure that we can scale up within an organization. So today I'm going to talk about design and cluster sizing. Before we even start installing things, we want to see what problem we're trying to solve, how we can design and size our cluster for our use cases. Then I'll talk about requirements and how we get a data science platform up and running on a number of machines. I'll talk about the architecture. To better understand the architecture means that we better understand how to architect a data science platform that not only serves the data science team, but all of the partners and other consumers of such data science organizations, whether that's people or applications consuming via APIs. Then we'll talk about installation targets on premises, on the cloud, and how we've designed Anaconda Enterprise to really run on any of these platforms. We've abstracted that away so you can focus on the security, governance, packaging, and providing that to data science users. We'll talk about high availability, how to keep things up and running with Anaconda Enterprise, and operational considerations. So what we're covering today is really a result of our rich conversations with our customers and users over the past 5-6 years in Anaconda Enterprise, and most recently with Anaconda Enterprise version 5. So some of the questions we get are, what are the requirements? How do I get it up and running? How does Anaconda Enterprise interact with external systems? Daniel talked a lot about Spark and Hadoop. We also work with Hive, Impala, HDFS, other databases, other online data sources. How do I install on-premises versus the cloud? How large should my cluster be for X number of users, X number of consumers? How does Anaconda Enterprise use a cluster? Why does it run on a cluster? How do I configure high availability? How does the Conda package repository and mirroring work? So I Conda install, but if I want to do that on premises, how do I do that? And then finally, things like core services, user-deployed apps, and what actually happens in Anaconda Enterprise when you launch a session or deployment. This gives us a better understanding of how that might work globally in an organization. So we'll talk about design and sizing. So Anaconda Enterprise is really about laptops, desktops, servers collaborating together. So it's very easy to spin up a Jupyter Notebook on your laptop and install dependencies. How do you share that? How do you collaborate? How do you collaborate meaningfully with notebooks and start to work with governed data science packages? How do you make sure that everyone's using a similar set of packages, even you might have developers on Mac, on Linux, on Windows, and different deployment targets? So when you deploy something, it means productionizing work that you've prototyped in the form of a machine learning model, REST API, maybe a web or mobile app, a notebook, and then we want to deploy that somewhere that's dependable, scalable, has the uptime we expect, and we want this all to be underlying with access control, authentication, auditing, because you might have to answer questions down the line about a certain model. You want to know what was done actually during the development of that model. So external connectors, it's useful to think about Anaconda Enterprise as fitting in between the administrator, the data science user, and we want to think about, on the left side, things like that an administrator or IT operations or OPSEC is thinking about. Identity providers, so Anaconda Enterprise connects to LDAP, Active Directory, SAML, Kerberos, as you expect, and helps you map that to who can do what on the platform and what data science, what data sources and remote computation sources you can connect to. Also on the left, things like persistent disk storage is going to become important later when we talk about high availability. So in that middle layer, Anaconda Enterprise is really providing you user management, Anaconda Enterprise Services, and we'll look at that in more detail when we talk about the architecture. Data science sessions and deployments. This is where the work's getting done. This is where the work's getting shared, consumed by other teams, possibly other BI tools, possibly other things that are doing model scoring. And finally, the nuts and bolts come to the database and storage. Where is that actually being stored? How is that being handled? And on the right side, we have, over the years, found all of the types of data sources. Our customers and users really want one place to do data science development and deployment in a way that can reach out to these many different types of data sources, compute sources, as a single kind of gateway to all of those different data sources, whether it be flat files or things stored in HDFS, Spark, Hive, Impala, SQL, NoSQL databases, Oracle, and things like Amazon S3, Azure Data Lake Storage, Google Cloud Storage. So there are native ways in Anaconda Enterprise to talk to all of these. Daniel did a great job explaining how we do that for one particular one with Spark, but we have a similar approach for many other data sources and compute sources. Daniel's talk focused on remote compute and storage connectivity for Spark. So this kind of connectivity lets you think about Anaconda Enterprise as you're architecting it. It doesn't depend on living next to or inside of these types of clusters, but it talks about how we have clean inputs and outputs to those remote servers, in this case Spark. So you can use something like Anaconda Enterprise to distribute Anaconda libraries across a Spark cluster. We have support for Kerberos with impersonation. You can interact directly with data in HDFS like Daniel showed. And this is just one example, but you can think about the many other types of data sources you might be connecting to and your data scientists might be connecting to. So if you put the operational IT hat on and think about, I'm provisioning a platform for developers to work on and do data science on. If you think about the design, cluster sizing, workload patterns, you have to, and we often help our users and customers think about operational considerations. If my data scientists are going to be running jobs, are they going to be CPU bound, memory bound, GPU bound, or some combination of them? So it's helpful to think if we are running remote computations on Spark and saving that data and then working with it inside of Anaconda Enterprise, what types of operations are they doing? Are they doing array-based computations, data cleaning, ETL tasks, or something like model training? All of these can be CPU intensive or IO intensive. And then there might be in-memory workloads that are memory bound. So we want to think about what data sets do we want to load in memory remotely on remote clusters, and what data sets do we want to bring in, a sample of the data set or a representative piece of that for training and test purposes. We also want to think about when you're serving out notebooks and dashboards and REST APIs, what's the back end of those? What are those things doing? Are they making remote calls out? Are they doing a lot of database queries? Are they doing a lot of cleaning and filtering on streaming data? What this really brings us to is what types of users and what distribution is that in your organization. So you think about an administrator, they have a high-level view that we're looking on the right of what is the total CPU on the cluster, the yellow line on top, what's the current utilization, how is that growing over time as I'm onboarding different teams. And then we think about the data scientists themselves, which can be, some can focus on model development, training, some could be focusing on the servicing of other developers or end users. And then there's repository users. This has always been a large group for us because this is where Anaconda Distribution meets Anaconda Enterprise, right? You think about, we have 500 users at the organization, and we want them all using secure versions, approved versions of libraries that are compliant with our open source policies. And then that brings us often to the largest group, which is viewers and consumers. So we talk a lot about the IT administrator, the data scientist, but we need to think about outside of that group, who are we serving to, and how will they be interacting with Anaconda Enterprise? So it's interesting, think about your organization, think about the distribution of users there, and that's really going to drive your sizing needs. So we might say, I have 20 data scientists and 1,000 consumers and 200 repo users. That might drive us to an initial cluster sizing based on some assumptions of what size of containers they're deploying. Maybe each one needs 2 CPUs, 4 gigs of RAM, and a GPU 10% of the time. That might lead us to an initial cluster size of 20 nodes, 16 cores, 100 gigs of RAM, something like that. That helps us get started, and then of course, on the ongoing basis, we can monitor and see how that activity matures in an organization as you have more consumption over time. So that's kind of the questions we think about during the design phase of Anaconda Enterprise. Then we get to the requirements. What do we actually need to spin these instances up? So from a very basic view, Anaconda Enterprise 5, you can think of it like your analytics cluster. So where all data science activity is going to happen, pandas, NumPy, plotting, training, all of that's happening inside of a big, think of it as one big abstract machine and a cluster. So each one of those nodes, think about a master node running the core services, and then you think about the worker nodes that are actually running the computations and where user sessions and deployments are actually being spawned on. And we'll talk about that in great detail in a minute. But if you think about a master node, we recommend 16 cores, 32 gigs of RAM. Often these will be much larger. These are kind of a baseline, given some rules of thumb. And if you think about disk space on the master node, that's where the persistent storage is being written to. And then your disk space on your worker nodes is where all the temporary ephemeral work is being done. So we put all that together, and you'll see when we get to the architecture diagram how this really falls into place on an actual cluster. In terms of system requirements, so Anaconda distribution has packages for Windows, Mac, Linux, Power 8, ARM. And you think about Anaconda Enterprise, you think of it as the server side where all of your analytics is happening on a cluster. So this is a Linux-based application. You can think of it very simply as an Anaconda Docker Kubernetes stack, and we'll show that in a moment. If you think about where it's installing to, it's Linux, Red Hat, or CentOS 7.2, 7.3, 7.4, Ubuntu 16.04, SUSE 12, SP2, SP3. These are versions that we test against that are proven for the security requirements and network and performance requirements of running Docker and containers in production with Anaconda. Disk requirements, right, because this is a distributed cluster that needs to keep in sync with each other. Usually SSDs are recommended, and there's certain IOPS requirements we'll talk about in the cloud section of what that actually looks like. File system, typical Linux file system types, and kernel modules that are supporting running Docker in production. Our documentation walks through this and more. And the good news is there's pre-flight checks in every Anaconda Enterprise installer that checks all this for you. Network and security requirements. When you're running an environment where you have many users, trusted users, running applications and containers, like for data science deployment, for data science development, a very common pattern in the industry for containerization and isolation is not only at the containerization layer like Docker and the orchestration layer like Kubernetes, but it's also in the network layer itself. So when you have things running, you might have 100 users, each user's running 10 applications. At this point, you think about how are we isolating and namespacing these different users, not only at the package level to make sure Python packages aren't conflicting, but at the network level and security level. So things like DNS A records with wildcards, TLS SSL certs with wildcards, and end-to-end SSL are all built into Anaconda Enterprise right when you install it. We have knowledge base articles and documentation about why we do this. The bottom line is for security and isolation. So you don't have applications accessing things from other applications. It's a very common pattern in things like Red Hat OpenShift and Pivotal Cloud Foundry. To follow this pattern, to follow all the most recent security standards. So now, with that kind of granular information in mind, let's talk about the architecture. And the better we understand the architecture of the platform that does everything in terms of data science and collaboration and deployment, we'll kind of dig in and see what makes up Anaconda Enterprise. So at the application level, it behaves like any other application that you might have at the enterprise level for Git servers or team collaboration. So at the highest level, it's a single file installer. You install it on one or more machines, and you interact with it from your browser. You dig into the functional level of what's actually happening behind the scenes. You see there's a user interface. There's authentication to make sure, authentication and authorization. And Anaconda Enterprise Services, this is both the core services and the user deployed apps and the user editor sessions. And then the database and storage layer. So if you look at the actual service level of the architecture, here's how Anaconda Enterprise does what it does all in one platform. And if you think about the user interface layer that we're interacting with, that we're showing in a lot of these talks and tutorials, below that is authentication. So this is where we're making sure they are who they say they are in terms of a user or data scientist or consumer. And then below that is we're actually requesting that I want to deploy a project, or I want to launch a new editor session to look at documentation. I want to store a package or a project. And I'll show some of that on the next slide of how that actually works. On the right side, you'll see sessions and you'll see deployments. Notice that it can be different languages and entirely different dependency trees for those projects. So for Python session in session 1, or session 2 is R, or session 3 is Spark. What this means is each time a user or many collaborators are launching sessions and working together, it's happening in its own container or its own pod in Kubernetes. And we're fetching all the dependencies and project code for that particular project, so this doesn't touch the framework installation of Python or R or Spark or any of that on the underlying machine. For deployments, it's the same story. We want to serve out a deployment. We want it to be isolated. And Anaconda Enterprise is handling all of the proxying and load balancing and ingress controller. All of that stuff is handled for you automatically. So you don't need to do this for every single session, every single deployment. And finally, when it hits the disk, it's going to go through a Postgres database or a Git server or object storage for project and state and package and file storage. So what does that look like in real life, in day-to-day operations? So if we take the same service architecture and we think about all the different types of users that are collaborating with Anaconda Enterprise, you have user A, data science user A launches a session. So they hit the UI, we make sure they are who they say they are, and they're authorized to do what they're asking to do. They want to launch a session. They want to open a new editor with Jupyter Lab or Jupyter Notebooks. And then we're going to create a container on behalf of them and say, this is your session, all transparent in the UI, and they now are editing files in their project. At this point, it's fetching the latest version or revision of the project from the Git server and from the repository. They're getting all of the Conda packages they need. They could be working in Python or R and have TensorFlow with C dependencies. They're just expressing what they need, and it's coming into the project so they can edit it. Then they share with collaborator B. So data science user B collaborates with user A. Data science user B looks at the UI. We make sure they are who they say they are. They query a session. They say, I'd like to work on that same project. And what's going to happen now is data scientist A is going to commit a change to their project. Maybe they push a new version of a model. User B gets a notification, immediately pulls that change in. User C, at the same time, wants to deploy a completely different project. So they go into the UI, they query the deployment service. This is all happening behind the scenes with that one-click deployment, right? So they're spawning a new deployment with R. Maybe they have a Shiny app that's calling out to Spark with Sparkly R, as Daniel mentioned. And then consumer viewer D only really has permission to view deployment, specifically deployment number 1. So they're going to go in the UI, ask the deploy service to view a deployment. And what this means is consumer D doesn't have Anaconda on their machine. They don't even know what Python and R is at this point. They're just being shared a deployment. Say, check out this app, and it has the latest model results, and you can see and consume what the data science team has been working on. And finally, we have repository user, like user E, who just wants to install and develop Python and R on their laptop using IT-approved and operationally approved packages. So they're going in, authenticating, hitting the repository service. They're basically using Conda as an end user, completely separate from the platform, using all the authentication and security in Anaconda Enterprise. Following that example of how Anaconda Enterprise works sort of in the wild, it's also useful to think about repository, because again, this is the overlap. This is where distribution meets Anaconda Enterprise. This is where we say we have 500 or 1,000 Anaconda users in my organization. How do we make sure that we know they're not using an outdated version of something or something that's vulnerable or something that lines up with our IT policies and open source policies? So over the years, we've learned, so up to now, we have about 1,400 plus packages for Python and R and their dependencies. And there's really 3 big methods for working with Conda packages. So you have the online Anaconda repository. This is what happens when you Conda install something. Conda install TensorFlow. It comes from repo to anaconda.com. This is Python packages that we build. These are MRO packages if you're using R. And what it means is when you have Anaconda Enterprise in one of the bottom instances running, you want to decide how you're consuming these online packages without having data scientists install directly from sort of this huge pool of packages. So the first way is to mirror directly from an online repository. So if you're running a cloud-based instance of Anaconda Enterprise, or if you're running an internet-connected on-premises instance, some of our customers will mirror the Anaconda repository with all of its versions and history, and then filter and say, I only want packages that don't have this license type, or only want the last few versions of this package. And What it means is they may do this quarterly, they may do this every 6 months, mirror those in, go through a security review, and then those are now the latest packages living on the Anaconda Enterprise instance on the bottom. Other customers are completely offline and air-gapped. Majority of our customers are, and that's why we ship Anaconda Enterprise as a self-contained single file that has everything I showed in the architecture diagram. We can also ship a mirror of our repository. This is different than Anaconda distribution because it's a historical mirror of all of the versions of packages that were built over time. So if you have older Python 2 or older dependencies, that's included in part of the mirror. And that's a big differentiator between any other data science development IDE. The third scenario is online package repository access. This means that you're installed in the cloud or an internet-connected machine, and you actually are okay with users connecting directly to the repository, doing what they're used to doing with Anaconda. This is a little more rare, but in that case, they may be using other parts of Anaconda Enterprise for governance and security and versioning. So with that architecture in mind, we want to talk about actually installing to different targets on premises or on the cloud. So we're going to talk about bare metal machines, both internet-connected and air-gapped machines, cloud-based instances for Amazon, Azure, and Google Cloud Platform. So Anaconda Enterprise can run on all of these environments, and the good news is we designed it from the bottom up, so it's the same footprint across all environments. So if your organization and some of our customers have a hybrid, they have an on-premises cluster, they have a cloud-based cluster, it's the same architecture, same exact process for setting things up, and the same design principles. So for an on-premises installation, this is what it looks like when you actually map those services to nodes. So if you look at the very left, Anaconda Enterprise Master, this is node 1, and here, this is where we're running services that write to disk. Object storage, database, Git, and we're actually writing to disk, and that's where we can do our backup and have things ready for a warm failover, which we'll talk about later. On nodes 2, 3, 4, and so on, these are the worker nodes for Anaconda Enterprise. So again, it's one place, one architecture. We're just installing and bringing up different nodes. And you can now see for the Anaconda Enterprise services, things like the UI, authentication, repository, these are actually running across the cluster. We're handling all the routing. There's some fault tolerance we'll talk about in the next section. And then editor sessions, we're spreading those out. The Anaconda Enterprise out of the box comes with Kubernetes, set up as a scheduler, and we're essentially spreading out those sessions, spreading out those user deployments, so that we're utilizing the cluster in the best way possible, and also spreading that out across the cluster, so we're not overloading or leaving machines idle. And you can see persistent storage on the master node and temporary disk storage on the others. For a cloud installation like Amazon, it's a very similar pattern. And here I've put up some of the recommendations or best practices or requirements and mapped those to a provider. So for Amazon, many of our customers are running in Amazon, and it's very simple. It's the same architecture mapped to Amazon EC2. We recommend instance types of M4 or now M5, 4x large or greater, with EBS volumes that have at least 3,000 IOPS or greater. We can help you map Anaconda Enterprise to a VPC security group. This is important for our remote data sources and remote compute sources. So if you have a Spark cluster, you want to be sure that your Anaconda Enterprise cluster can communicate to that. You can use things like Route 53 for DNS configuration, or have a CloudFormation script that helps you set all of this up in one bang. So it's the same concept, master node running with persistent disk storage, and worker nodes that are also running on EC2 instances. Same architecture on the cloud. For Microsoft Azure, same story, no big changes. On this case, you'll be using D16 or greater instances. We're partnered with Microsoft and many customers running in production on Azure. You're going to want to use a P20 storage disk, which gives you the right amount of IOPS for Anaconda Enterprise to make sure it's responsive and performant. You can use things like Azure Virtual Network to define what Anaconda Enterprise can reach out to in terms of what communication happens inside of the cluster and what communication happens external to that in terms of usage and consumption. And things like Azure DNS make it very easy to spin up wildcard records and get things configured for end-to-end TLS and wildcard DNS and certificates. For Google Cloud Platform, we have customers running here as well. You can use an N1 standard 16 or greater instance. You can use an SSD disk. You can define a VPC network in Google Cloud and use Google Cloud DNS for DNS configuration. Same architecture. You see the theme here. It's not changing with each provider. It's the exact same footprint, both for the across cloud vendors, but also across upgrades of Anaconda Enterprise. And at the top, I mentioned Google Cloud Launcher. You can search for this and get up and running with Anaconda Enterprise either as a 30-day trial or as a full-blown production installation in 5 minutes. And we'll be adding these kinds of templates to other cloud providers very, very soon. So you can do the same thing in Amazon. You can do the same thing in Azure. So very excited about that. The installation process is very straightforward. Like any enterprise application, there's the pre-installation requirements checks. So I mentioned earlier the CPU, memory requirements, kernel modules, disk requirements. We're checking all that for you as part of the installation process, and we'll flag on every single node. We'll check and make sure that those are set correctly to prevent data loss and to ensure performance. This is typically the point where you're acquiring DNS records and SSL certificates, TLS certificates. The installation itself, initially, you can choose between 1 and 4 nodes. At any time after that, you can grow your cluster along with your usage. So post-installation, it's basically one step. You say, this is the DNS name that I'm using, and we take care of the rest. At that point, you can install additional worker nodes. There's a single command. I'll show that later. You configure your TLS certificates, configure your channels, and this is the point where you want to decide how you're going to consume Anaconda packages via mirroring, and then onboard the users and get them spun up, get them with the right role-based access control mapped to your organizational needs. Next is a big topic for us, high availability. For onboarding so many repository users and collaborators and consumers, how do we make sure that Anaconda Enterprise is up and running all the time as much as we expect it to? So you ask the questions of, when you're thinking about high availability for your organization, there's no standard, it's different for every organization, but we think about what are the uptime requirements, how do we prevent the downtime of AE in production of either the repository or sessions or long-running deployments that other applications or people are consuming. And you think about what happens if one of the worker nodes I showed with services, deployment sessions goes down or becomes unresponsive, either temporarily or for good. What happens if the master node goes down? How do I back up and restore that? What do the times look like for that? So I'm going to show you how to do high availability with Anaconda Enterprise today. The first thing I'll talk about is fault tolerance. This is all out of the box with Anaconda Enterprise, and I'll show this on a diagram in a moment. But it means Anaconda Enterprise has service redundancy, fault tolerance, monitoring, all out of the box. So you don't have to worry about this. It means there's automatic service restarts, health monitoring. So for core services, things like authentication, things like the UI, these services will automatically be restarted either if the service goes down or if the node they're on, the worker node, goes down. Those are migrated, spun up. We handle all the routing. There's basically zero config in the case of fault tolerance there. For user deployments, right? Maybe I deployed something, it's available at a certain endpoint, and I have 10 or hundreds of applications or consumers using that. If that worker node goes down, again, that's spun up elsewhere, and users continue to consume it at the same endpoint. This is also true for worker nodes in themselves. So if a worker node becomes unresponsive, it's flagged immediately, no more traffic is sent to it, and all of those services, both core services and user services, are immediately spun up on other nodes in the cluster. So this is something that IT and operations folks like in terms of availability and the lack of manual intervention. So what does that look like on a diagram? It looks like this. So this high availability in Anaconda Enterprise today, it means that you have redundancy of Anaconda Enterprise, of Docker, of Kubernetes, and the state of your entire cluster as the analytics are happening on this cluster. So on node number 1, the Anaconda Enterprise Master, you have your object storage for package and project storage, for package storage. You have database for cluster state. You have Git storage for projects. And then you'll note throughout there's kubelet and Docker. This is basically saying for each container, whether it's a core service or a user deployment, this container should be in this state on this machine. So maybe it's running a Python API, or maybe it's running a notebook with R. It's a known state. And Docker is where the containerization is happening for each of these services. etcd is a distributed key value store. And then the Kube API server on the left side is how all of the internal Kubernetes requests are happening. So what I'm showing here happens out of the box when you install Anaconda Enterprise on n number of nodes. The first one is the master. This is the persistent disk storage where we're doing all of our backups for a warm failover. And the nodes 2 and 3 are Kubernetes masters. This means that if node 2 goes down, we'll still be able to make requests to the Kubernetes front-end API on nodes 1 or 3. In the case that etcd goes down, which is the distributed key value store for all cluster orchestration, we still have a distributed key value store running on one of those nodes. So it's a very common pattern for Kubernetes to have 3 or 5 or 7 master nodes, and this is how Anaconda Enterprise installs out of the box. For the worker nodes, I already talked about that fault tolerance. So pick a node, take it down, and we're still good. We're still running. Kubernetes is still running. Docker containers are still running. If needed, they're migrated to another node. We handle this all automatically out of the box for you to keep those core services and sessions and deployments up and running and handle all the routing and load balancing automatically. So in summary, high availability. I like to read the Kubernetes documentation. It describes high availability as putting on a pair of pants with a belt with suspenders over a pair of pants with belt and another pair of suspenders. So we make it very easy out of the box to not have to go through that routine and to leverage the latest and greatest industry standards for high availability because we know how much people depend on Anaconda in production. So it comes down to a master node with persistent storage. It's also running a distributed key value store with a front-end API server, Kube API server for Kubernetes. The 2 Kubernetes master nodes managed by Anaconda Enterprise are also running etcd and Kube API server. Those 3 nodes make up high availability of the Kubernetes cluster. You don't have to bring your own. It's all included and managed by Anaconda Enterprise. The backup and restore on the master node is about a 30-minute process, similar to when you add a new node. This is simply taking a backup snapshot, which is project storage, package storage, cluster state, and all Kubernetes state, putting that into a tar file so you can put it into a scheduled backup script that you're typically running daily or hourly. And at that point, if there's a failure of one of those master nodes, your cluster continues in production, and you simply bring up a new master node, which has the qualities from the previous diagram. You can also configure with DNS failover. It's very common to say these are my 3 master nodes. DNS is either round robining or aware of the state, the status of one of those 3 nodes. And then your n number of worker nodes are essentially expendable at this point. So if you have 10 worker nodes, something goes down, all the services are migrated, and you can add a worker node at a later time. So the last section I want to talk about, armed with all this information, is operational considerations. Sort of once you're done installing, once you're done with the design, how do you then iterate and increment on top of that to keep providing to your data science users' needs and your consumers' needs? So the first thing is about user management. The first thing that typically we do right after an installation is to hook into your external identity provider to LDAP, Active Directory, SAML, Kerberos, support all the latest and greatest protocols there. And this is also where we sit down with the operational team and say, what are the different roles? How do you define an administrator? How do you define a data scientist? And who can do what on a service-to-service basis? These could be different teams, these could be different organizations that have rights to different resources, for instance. So we'll help you with that mapping exercise. It's a very useful way to say, here's how I define users and groups in our identity provider. Here's what I want to do in Anaconda Enterprise. Roles are very helpful here. You can think of them like composable groups. So you can either map directly to your groups if that works for you with that rigid definition, or you can use roles to go beyond that in a composable manner to say who can deploy things, who can create projects, and so on. Cluster monitoring, I mentioned before, you're monitoring utilization in terms of CPU, memory, disk, disk-based network traffic across the entire cluster. So you see if something is misbehaving, you see if something's particularly overloaded, which Kubernetes should be handling in terms of Anaconda Enterprise services. You can also, almost all of our customers use this as a way to determine when to procure new hardware. So as usage is increasing, they might have a plan to onboard 200 users per quarter, per year, 500 repository users, and X number of consumers. And what this does is gives them a kind of a watermark to say when cluster utilization or memory utilization hits 50% or 75%, we will then trigger procurement of new hardware to keep things up and running, and we don't get delayed by those procurement delays. And so this is a really useful way to do that. There's you can send this to your log forward this to your existing logging tooling around that. You can also have alerting whether nodes or cluster conditions are met in terms of high water marks on any of these metrics. Cluster expansion. This is something really easy to do in Anaconda Enterprise, and we want to help grow with your usage, whether it's data scientists or consumers. It's very easy to expand your Anaconda Enterprise cluster with a single command that looks like this. From the Operations Center, you choose a new worker node, click continue, and you get a one-line command to run on a fresh machine. No configuration required beyond that. So you can combine this with your favorite configuration management tool, spin up a new node upon certain conditions, and have that automatically join the Anaconda Enterprise cluster. And as soon as it's up and running in about 20 minutes, it'll start receiving. It's now a candidate for sessions and deployments. So very easy. We've come a long way from cluster management in terms of manual intervention and configuration. Cluster logging and auditing. This is a big one because remember, you're running a dozen Anaconda Enterprise services, repository. Everything has logs. We want to know what happens when things go wrong or there's security issues. This is also true for all of the tens or hundreds or thousands of editor sessions of deployments. And so we provide a centralized search for all cluster-related activity and audit logs for all user activity. So basically, you can think of a case where there's misbehaving TLS SSL certificates. We want to see what's misconfigured. One place to go. If you want to see which deployments are spinning up with a given package, maybe an outdated package, you can see which deployments are consuming that and bump that version in the repository and see how that's getting dispersed across the cluster. Those are just a couple of examples, but there's lots of things, rich information coming from a data science platform in terms of both the operational side and the actual consumption and data science development side. So in summary, if we take all the things we learned about cluster design, operational considerations, high availability, and the architecture itself, these are the big takeaways that we've learned with Anaconda Enterprise, especially our latest architecture. So number one, and probably the biggest point, was that Anaconda Enterprise, specifically version 5, uses a consistent architecture across all types of deployments, whether it's bare metal or bare metal air-gapped or cloud-based on one of the 3 providers I mentioned. Same installer, same approach. You don't have to think about mapping that to mapping different architectures across different infrastructures. It's common across that and across upgrades. So as we upgrade Anaconda Enterprise, if we add services or upgrade services, it's all done in place without changing that footprint every time. You also really want to think about your end users and what the data scientists are going to be accessing in terms of databases and remote clusters. So if they are accessing Hadoop and Spark cluster, you want to think about whether they're in a place where they can use K-init for Kerberos, and you want them to basically have the same authorization access control they have in their Spark cluster from AE. That's all possible, and you just need to think about the interconnect between those in terms of network paths and data flow of what might be queries between the 2 clusters. Or, like I said before, if you're using Anaconda Enterprise and you're accessing an Oracle database, NoSQL database, and Amazon S3, all of that's possible. It's just something to think about when you're designing your virtual network on the cloud or your subnet on premises. Package mirroring is a big deal because it means how you get Anaconda distribution to your hundreds or thousands of users and manage that in one place. It really makes the parity between I'm working on my laptop on behalf of an organization, I'm working on Anaconda Enterprise with my team, or I'm working on a Spark cluster. I really want to know as an operational IT administrator that there's parity between those versions. They want to match it up to the versions that we support and the versions that are compatible with our open source compliance and policies. So choosing the type of mirroring, the frequency of mirroring is a very important step because that means how you're operationalizing Anaconda libraries and consuming them in your organization. Ongoing monitoring and metrics are key for 2 things. For cluster utilization, we want to know that the money we spent on the cluster is being used well and wisely. And secondly, we want to plan for future expansion. There's a funny Anaconda effect that happens if a data science team starts using Anaconda. Others see that and want to kind of get in on the game and stop emailing notebooks to each other and stop kind of side-loading packages, whether it's R or Python. And so people start asking, hey, how do I get access to the cluster? How do I consume? How do I get an account on there? And so we want to grow with you. We make it very easy to expand. And it's not a big deal when you want to add 1 node or 5 nodes or 10 nodes to meet up new team demands and data science demands. And finally, the big one is because we're having so many people depend on Anaconda as an operational and productionized environment for analytics, data science, Python, R, Spark, and it's sort of the glue language. Anaconda Enterprise is sort of the glue platform that brings all these teams together and lets data science have an impact across teams outside of the data science team and have other people really getting the rich information and insight that's being produced from the team. So high availability and fault tolerance are available out of the box as part of Anaconda Enterprise. Because we want to keep our customers up and running with the latest and greatest, and have them do that in a way that is manageable for their organization. So with that, I'll take any questions about Anaconda Enterprise architecture deployments, and thank you for your time.